Now that we've learned the two concepts of node degree and connected components, we could start to apply them immediately to the dining table's partner data set and see what insights we can get out of it. First, let's look at degree. Now we have some choices. This is a directed network, so we can look at in degree, out degree, or just undirected degree. Now why doesn't out degree make sense? Well, every girl is naming two other girls as her first and second choice, therefore all the nodes are going to have the same degree, same out degree. So we don't want out degree. In degree, on the other hand, is a lot more interesting because it's a reflection of popularity. If lots of other girls want to sit with you at the same table, well, that says something about how desirable you are in this girl's dorm. So let's look at that. The degree is calculated automatically, so you can just go straight to ranking and click on nodes and then choose in degree. Now we could color the nodes by in degree, but we're going to save color for the connected components. So let's instead look at size. It's this little diamond shape here. So I'm going to click on it and we can choose the min and max size. I'm going to go, since these nodes are sized 5, I'm going to set the min size a little bit lower at 2 and the max size maybe twice that. There is this option called spline, and this just says how does the size vary as this quantity of interest varies, in this case in degree. Since the inequality in popularity isn't that large and it's a relatively small network, this linear relationship is okay. However, if, for example, you were looking at a massive network, a directed one such as the web, and, well, you wouldn't be looking at the whole web, but say a subset of the web, and there could be one page that has 100,000 in links and many other pages that have one in link or no in links. And you wouldn't want a node that's 100,000 times bigger than other nodes. It would obscure your whole visualization. So in that case, you may want to do something like a log linear relationship, something like this. But for our purposes here, we're just going to go linear. So let's apply that. And voila, instantly we can see that some girls are more popular than others. Marian and Eva look like they're most popular, and Hilda doesn't seem to be doing too poorly either. Now, this is all visual, and if we want to actually look up the numbers, what is the in degree of each node, if we simply go to Data Laboratory, unfortunately, it doesn't populate the degree automatically. So we're going to go back to Overview, and we're going to ask it to calculate the average degree. Now, the average degree is 2, which we sort of knew because we have 52 edges and 26 nodes, so you can divide one by the other. So nothing surprising there. It has given us the degree distribution. We're actually interested in the in degree distribution. And here you can see that, for example, 2 girls have in degree 6, but I don't know, 9 girls have in degree 2. So that's interesting in and of itself. However, what is super nice about this is that we can go back to Data Lab, and now we actually have the in degree. And clicking on top here, or this sorts lowest to highest, let's click again, and we have the 2 girls who have in degree 6, who are Marian and Eva. So that's a nice way of just getting at the numbers, and also if you're interested in the degree distribution, you can have a quick look like this. Of course, you can export this spreadsheet and analyze it further as well. So back to the overview. What we have is a picture where some girls are more popular than others, but we don't really know whether there are certain cliques or how information might flow. So I'm going to start out by asking the question, if someone had some piece of gossip, one particular girl, where could that gossip go? Or if you had a set of girls, would they all be able to hear gossip from everyone else? And this is precisely the question of who is in the same strongly connected component. because if you're in the same strongly connected component with someone else, it means that anything that they find out can potentially make its way to you. So let's find the strongly connected components. So I'm going to go back to the statistics tab. If you have filters instead, just make sure you click on statistics. And I'm going to click on connected components. I'm going to say run. And it's going to ask me if I want the strongly connected components, which I can get in a directed graph or not. And yes, I do in fact want the strongly connected components, because if you imagine the flow of information, if one girl says she'd like to sit with someone else, but that person doesn't want to sit with her, well, they may also not be willing to share information with her. So we really want to take into account the directionality of the edges. So I'm going to say OK, and it's telling me there's one weakly connected component, which just means if we treat the edges as undirected, everyone's connected directly or indirectly, which is true, right? We just have a single connected network. But it's telling me that there are actually 11 different strongly connected components, meaning that information wouldn't circulate throughout the network following directed edges. So we're going to close this, and now let's color the nodes by the strongly connected components. So I'm going to go to partition here, and I want to partition the nodes, and I'm going to click refresh to just get this new partition, which should be the strongly connected ID. And it's giving me some colors. Some of these seem a little bit similar, so let me just see. I'm going to right click and say randomize colors, and these look a little bit different, so I'm going to apply them. And I think this paints a very, very clear picture about the dynamics in this among this group of girls. So first of all, we have the purple cluster here, where all of these girls may be sharing information with each other, and they also include these two very popular girls, Marion and Eva. You see this one girl here, Alice, who names two girls in this cluster, but her color is actually different. She's in a strongly connected component all by herself, because actually no one selected Alice as someone they wanted to sit with. We see this little component here of 3 nodes in blue. Betty, Hilda, and Hazel all had, well, Hazel had selected Hilda and vice versa, and Betty had selected Hilda and vice versa. So they form one strongly connected component. A similar dynamic with Jane, Mary, and Edna. And here is an example with Helen, Jean, and Robin. So here you actually have a closed triad, but what has happened is that Helen and Jean mutually chose each other, and then Jean chose Robin as her second choice, and then Robin chose Helen. So you can kind of circulate in here, and then Ada and Cora are their own strongly connected component because they chose each other. So this shows you a bit of the dynamic of girls in at earlier stages of their lives, but also there's some recent research showing that most social networks, when you're naming friends, tend to be fairly asymmetrical like this. And in this case, because it's a relatively small network, etc., even just looking at the strongly connected components without applying community detection algorithms, which is something that we're going to be doing later on, we can figure out a lot of the dynamic between the girls.